Okay, once again, good afternoon, everyone, and welcome to the fourth and the last session of this NCOBA Junior Round 2 training program, which is designed to assist students to tackle the second round of the Junior Olympiad 2021. We have been at it for the last 3 weeks, and this is the last session. Today is the 13th of May, and you write the 18th of May. So even before I start, I want to wish you all the very best for the forthcoming test. I'm sure that most of you are well prepared now, with having had a lot of training. Almost by the time we finish today, I think you will have at least 60 problems which have been chosen from past round 2 papers. Today we will do the same. We will do some other problems as well, which haven't come necessarily from round 2. The problems were posted. I think they were posted yesterday morning or late on Tuesday. So you've had a little time to tackle them. Hopefully you did try the problems. Okay, so let's go straight to this. If there's anything that people want to say at the moment, I'll give you a chance to say. Is there anything you want to ask? All right, so let's go. Let's get ahead. We now want to go on to sharing the screen. All right. Ooh. Okay, so let's go. As you can see, we are doing selected problems from round 2 junior papers, and we've got some problems which we've chosen from the book 1000 Mathematics Olympiad Problems. All right, let's go straight away to the first problem. Just give me a chance to get used to what's going on here. Sorry, my mouse is playing up. Not sure what's going on here. Okay, so at last I'm on track. Okay, the very first problem, you'll see we are doing the 21st problem of the 2018 paper. Last week we went up to the problem 20, so we go to problem 21 now. And this problem here is a problem on areas, and as you can see, it is asking the area of a rectangle. Let's read the question. The diagram shows a rectangle inside a circle, as you can see. The rectangle just touches the sides of the semicircle, as you can see. And 2 lengths are shown. You are shown this small piece here, which is 1 centimeter, and that piece there, which is 4 centimeters. And using that, you are asked to find the area of the rectangle in square centimeters, obviously. Okay, so let's see. To find the area of a rectangle, the area of a rectangle is length times breadth, as we all know. So we need to work out the breadth. We've got the breadth is 4. We need to work out this length here. Right? Now we do know that this is a rectangle, so we can put a 90 degrees here. Like that. And so how do we find this? Okay, now that we've got a 90 degrees, means we've got a right angle triangle here somewhere, and that surely should help us to find that unknown side. So what is a right angle triangle? Well, you just have to complete the hypotenuse, which is not drawn. So the creativity here is that you got a 90 degrees here, you got a 4 here, and you got this length here. And you would be able to get this length if you join this. Right, so this becomes the hypotenuse. Of the triangle. Now, so how do we find that? Well, perhaps what we can do is to use the center of the circle. The center of the circle will be halfway in between here. Let's identify the center. And we have not only this triangle, but we also have another one, which is joined from here to the center. Let's do that. We join this to the center here. Okay. In that case, we have a radius. And we might be able to work that out. If we know that, then we know this, because this will be twice this, see? This is right in the middle. Okay, so let's try to calculate this thing here. Now, the hypotenuse of this triangle is the radius. All right, and the other side, we've got 1 is 4. This is the hypotenuse. We don't know this, but a little thought will tell you that the distance from here to the boundary, this thing here is also the radius, which means, and we know that this is 1. See, now that 1 becomes useful here now. So it means that this piece here is the radius r minus 1. Okay, so now we have a right angle triangle. You've got 2 sides which are unknown, but they are both in terms of r, and the third side is 4. So you can use Pythagoras to get an equation involving the 3 sides of this right angle triangle. Pythagoras says 4 squared oh, sorry, I wiped myself out. 4 squared plus this part here, the other side of the right angle triangle, r minus 1 squared, is equal to the square on the hypotenuse, r squared. All right, and now we can work this thing out. It's 16 plus, when you're squaring a binomial, you square the first term, r squared, and then you multiply these two. R times negative 1 is negative r, and you must double that. It becomes negative 2r, and you square negative 1, square it, it's plus 1. So remember, this is not r squared plus 1. There is a middle term, which is twice the product of these two, which I've written down here. And that is equal to r squared. You can see the r squareds will cancel off. And you have that, bring all the r's to one side, and you got minus 2r is equal to minus 17. Right. And therefore, your diameter, your r, is equal to 8.5, 8.5. Okay, so this is r minus 1 will be 7.5. That one. And then you have to double that to get the other side. So, so this is 7.5, and the double of that is 15. This is 15. And the area is 15 times 4. Somehow, I'm taking too long over this thing. It should be much easier than this, and I'm not sure whether the answer is right as well. So the area of the rectangle is 60. Okay, let me just do this thing a little bit more slowly. You find the radius. Once you find the radius, then we have the area of this rectangle is 4 times this length here, and this length here is the 4 times this length here, and that is the radius minus 1, which is, we calculated the radius to be 8.5. You subtract 1, you get 7.5. Double it to get this thing here, 15, and that's what the breadth of this, the length of this rectangle is. It's 15. The area is 15 times 2, which is 60. Okay, now let me just see why I took such a long time over this. I'm sure there was a much easier way, and maybe the area is 60. Oh, okay. Oh, okay, it's the same thing. All right, so that's the solution to that first problem. Let me go on to the second problem. It looked easier than I thought, but I did exactly the same thing. So let's get on to problem number 22 now. Okay, we're going, as the problems proceed, you will become more and more difficult until it comes to 25. So let's look at this. This problem says determine the sum of all integers x which satisfy the equation this. Now this problem, you got a power, and the power is equal to 1. Now, which number raised to a power is equal to 1? There are only two possibilities. 1 raised to any power equals 1, right? I'm saying n is the index. Or even minus 1 raised to an even power gives you 1. Okay? So, and there's a third situation where the index or the exponent is 0. When the exponent is 0, then again, anything raised to the power of 0 is equal to 1. So there are 3 possible cases here. So let's find out. They say determine the sum of all integers x which satisfy this equation. So the first one is where the base is 1. So you have 218 minus x equals 1. Right? And it doesn't matter what this index is. As long as this is 1, then you will have. So when you solve for x here, you will see that x, if you take it to the other side, or take it to the right-hand side, that's x. And the 1 goes to the left-hand side, which means 218 minus 1. That gives you 217. Anyway, 218 minus 217 is equal to 1. Okay, the other case is where you have the base is negative 1. So you could have 218 minus x equals negative 1. And this time, when you solve for x, you bring x to this side, then the minus 1 becomes plus 1 when you take it to the other side. So you got 219. All right, so you could have x equals 219. And you have to just check here. When x is 219, you'll see you got 221 plus 219, and that is 440, and that's an even number. So that's fine. See, so when x is 219, this is even, and this is -1. So x equals 219 is one of the x's. And finally, when the exponent is 0, the exponent is 221 plus x equals 0. That's your exponent. And in this case here, you have x is equal to -221, right? And now the question is find the sum of all the integers x, which makes this equation true. So there are 3 possible values: 217 plus 219 minus 221. And 219 minus 221 is -2. So it looks as if the sum is 15. 215. So this is the answer that I get. Let me just check to see whether this is what I got here. All right, I got 215 at the end of this. So I am on the right track. Okay, so that is how you do this problem. Let me just find out. Guys, by show of hands, can you indicate to me how many of you have got this problem right? By now you know how to show your hands, I presume. So the 21 people who have raised their hands, okay, that's good. To get all 3 cases is not an easy thing. You may get 2, you might miss 1. All right. So well done, guys, whoever got this. You've solved problem 22, which is a difficult problem. Okay, so let's get on to problem number 23. All right, problem number 23. This evidently is a problem on speed, distance speed. Very often you have these kinds of questions in an Olympiad problem, and usually learners find these problems a little bit challenging. We have done a couple, and hopefully you are getting an idea as to how to go around solving these problems. The important formula is speed times time equals distance, right? 40 kilometers per hour means 40 kilometers in 1 hour. If you say a car is traveling at 40 kilometers per hour, it means in 1 hour it covers 40 kilometers. That's the important thing. You can work out the distance. All right, now those who have raised your hand, you can put your hands down. Thank you. Let's now get on to the next problem. To find out, read this problem and find out what the problem is all about. Tom was jogging at a constant speed of 10 kilometers per hour on a straight road. So let's just draw the road so we have an idea of what he was doing. So what is he doing? He's jogging away on a straight road. Jerry, jogging at a constant speed, is 600 meters behind Tom. So you've got Tom is, okay, suppose they are going in this direction. So Tom is 600 meters ahead of So Tom is here somewhere, and he's ahead. They're going in this direction, and Jerry is somewhere here. Okay, I don't know. These guys are playing a cat and mouse game here. I don't know whether you read comics, but Tom and Jerry was one of my favorite comics. But there's something funny here. Tom shouldn't be leading. It's normally Tom who is chasing Jerry, so he should be behind him. So whoever set this problem have been a little bit unrealistic. You don't get mice chasing cats. Anyway, he is traveling at 12 kilometers per hour. And Tom is traveling at 10. Okay, so this cat is trying to catch hold of the Tom. Now they are 600 meters apart. Okay, that's what they say. Now, how many minutes would it take Jerry to catch up with Tom? Obviously, he's going to catch up because he's traveling at a faster rate than what Tom is. So how long would it take to cover the 600 meters? Now, actually, this is quite an easy problem because if you think about it, he's traveling 2 kilometers faster than that. It's because of his 2 kilometers extra speed that he is able to catch up. So what you've got here is, you can think of his, he needs to cover, needs. Yeah. I'm sorry, no, I need to change this. Can you all see the screen? Am I? Hello?
Yes, sir.
Oh, you can.
Yes, sir.
I thought somebody was complaining.
Yes, we can.
Okay, thanks. Thank you. Thank you very much. Okay, now he needs to cover 600 meters traveling at 2 kilometers per hour. And that's important, traveling at 2, because he's traveling at 2 kilometers faster than the fellow. So this extra 2 kilometers is going to help him to cover that additional distance. See? So once you settle on that, then you can see how long it's going to take him to catch up with him, right? So, so he's going at 2 kilometers per hour in 60 minutes. Right, per hour, 2 kilometers, 60 minutes. He wants to cover 600 meters. Now 2 kilometers, let's convert that to meters. So it's 2,000 meters in 60 minutes. But he wants to do 600 meters in how many minutes? So you can see this is a ratio problem, a proportion. A lot of problems are just simply problems on proportion and ratio, as long as you understand what the problem is. So now it becomes easy, because if he does 2,000 meters in 60 minutes, 600 will just be 600 over 2,000 times 60. And obviously, right, it will be a shorter time because it only needs 600. And that is 6 over 20. These cancel. And even this thing here cancels. That one, the 10 there. The 2 goes into 6 3 times. And you got 3 times 6 is 18. Now remember, this is minutes. Okay, because 600 meters in how many minutes? So the answer is 18. Okay. So the idea was to recognize that you are actually using that additional speed, 2 kilometers per hour, to cover that distance. And once you identify that, then there is no problem. I have an alternate method of solving this, and I'm not going to go into detail with that. When you, let me just clear these drawings. So that's how you get this 18 minutes. And the second method is where most people will do it like this. I'll start like this. Suppose it takes T minutes for Jerry to catch up with Tom. Right. Your question is how many minutes does it take him to catch up with Tom? So you say, let your unknown be T, and I need to calculate T. So you need to get equations involving T. So let's see. What does Tom cover in time T? You need to know how much Tom covers in time T. Remember, Tom is in front. He's traveling at 10 kilometers per hour. So in 60 minutes, he travels 10 kilometers. And we were talking about T minutes, right? So in T minutes, he will cover T over 60 times 10. Right? That should be quite clear. In 60 minutes, he does 10. In T minutes, it'll be T over 60 times 10. And you get a thing in T here. In the meantime, Jerry, but he's traveling at 12 kilometers per hour, right? And you see how much he covers, and you see the same calculation, you'll get T over 5, right? But Jerry now is going to catch up with Tom. He travels T over 5 kilometers, right? And he travels T over 6 kilometers, but they were 600 meters apart. Remember, T over 5 is smaller than T over 6. These are in kilometers, right? So T over 5 is smaller than T over 6. I'm sorry, T over 6 is smaller than T over 5 because Jerry covers a longer distance. So the difference between these two is your 600 meters. This is a critical equation, right? Because he needs to cover the additional 600 meters. So to catch up with him, he has to, this difference in the time will be, the difference kilometers will be 600. Okay, and there again, when you got an equation, there solve for it, it's 18. This is a little bit more difficult method, but if you did my method, the first method, it's very nice and easy. Okay, so let's just find out from the learners, how many of you were able to, distance time problem is usually, people find it quite difficult to do it, but I'm happy to see that there are a number of people who have actually tackled this problem and who have solved it, which is quite encouraging. All right. So the 11 people, which I'm very happy about. Okay, so the next problem is now we go on to problem number 4, is it? Problem number 24. Problem number 24 is a clock problem. It says that this clock works correctly, but the numbers are missing. Normally, in a clock, you have, it's looking like this. Nowadays, you have digital clocks, so sometimes some of you guys might not be familiar with it, but it's important for you to know what the digital clock, the old clock that I grew up with. It's a circular clock. And you have numbers. I'm sure all of you have seen this. You have starting from the top. You have number 12 here. And then you have 1, and 2, and so on. Right down here you have 6. And it goes on like that. And then your hour hand, right? It points. Oh, let me just draw something decent here. Sorry about this. The hour hand is a longer hand, and then you got the, I'm sorry, it's a minute hand, and the hour hand is a shorter hand. And every time this thing goes around a full circle, the shorter hand goes through 1 hour, right? But that's important to know. The minute hand covers 1 hour, it goes through a full circle, and the hour hand only goes through 1/12 of a full revolution in 1 hour. Anyway, I'm not sure whether these matters are important, but here's the position that the whole clock has rotated. So you don't know where the 12 is, right? And you got a number here, A, and you don't now it's really weird because it's very difficult to know what the time is if you don't know where the 12 is. So you don't know where the 12 is. So that's a little bit disconcerting. But they say use the positions of the hour and the minute hands to determine which hour is represented by the letter A. Now, I have to admit that I struggled for a bit with this problem until I realized something quite nice. The logic here is that, watch the hour hand. And this part here is drawn. And it's exactly a 3. In other words, the hour hand has moved from the previous hour. It takes 1 hour to go from here to here, right? The hour hand, not the minute hand. It takes 1 hour. But if you look at this, it has only traversed 3, exactly 3 of these 5 units. Right? So, in time, this is 1 hour. So in time, what would this be? It will be 3/5 of 1 hour. And 1 hour is 60 minutes. I'll repeat that. An hour hand to travel from 1 hour to another goes through 5 of these units. At the moment, it's only done 3 of these units. So in other words, it's done 3/5 of an hour, which is 60 minutes. And if you do 3/5 of 60, 5 goes into 60, 12 times. 3 times 12 is 36. So in other words, the hour has actually traveled. The time is now 36 minutes past the hour, right? 36 minutes past the hour. Now, where is 36 minutes? This thing here is at 30 minutes, half an hour. 7 will be at 35. And 8 will be at 40. So 36 minutes will be here somewhere. 35, right? And we want to know what the next hour is, you see? This is the minute hand. And the next hour will be here. So you can see it has to be 8. This is, so the time now, 36 minutes past means it's more than 25/2, right? And it has to be so this minute hand is moving towards what number? We want to know where is the minute hand moving towards? It's moving towards 40, which is represented by the number 8. So the hour that is represented by the letter A is 8. See, it's quite simple, but it's a strategy which I haven't seen before, and it took me a long time to get this thing out. I'd like to know how many of you actually, there are at least 4 people who've got A equals 8. Oh, you people are much better than I am, because I struggle with this. Very nice. Okay, good, well done. Okay, those of you who didn't get it, consider that you have learned something, right? And and the logic of this is very nice. You examine the context and you ask yourself what's going on and try to interpret that in terms of some figures, as I have done. Right, so we now go on to the next problem number 25, which is the last problem of the 2018 round 2 paper. We've done 2020, we've done 2019, and we are now finishing 2018, which is very satisfying. And now here you got a area problem. Let's have a look at this and see what they are saying. They're saying a 10 centimeter by 6 centimeter rectangle. So the length is 10 and the breadth is 6. Is divided into 5 smaller rectangles. Okay, you can see here it is, all the divisions along the length, 1, 2, 3, 4, 5, and you got smaller rectangles. Okay, and then now obviously it's 10 centimeters by 6, so this is 6 here, and this whole thing is 10, so each of these is 2. Right? It's 5 smaller rectangles. Okay, as we read through, put the information in. Don't read the whole thing and then put the information. You'll never be able to do it. Do it step by step like the way I'm doing now. So you've got 5 smaller rectangles. This is 10, so each must be 2. The diagonal AB is joined. So we can calculate the length of the diagonal because it's you got a Pythagoras, AB, you know this and you know that, 6, 10. So you can calculate length of the diagonal, but I'm not sure whether that is required. As well as a number of smaller diagonals. Now let's see now. Oh, no, these are not really kind of diagonals. Oh, here you are. Okay, these are diagonals. So this is the diagonal of a smaller rectangle. Let's complete that. They say that these are diagonals, so let's just complete the maybe I should use a different color to highlight this thing. Right, okay, that's red. And this is another small diagonal, so you got so these now we can see, they say smaller diagonals, and you can see exactly which rectangles these are, right? For which these are smaller, or for which these are diagonals. Right. How much larger is the shaded area than the unshaded area? Oh, now this is really weird. The shapes now become really right. Now I can't find the area of the shaded part, but for instance, this area I already know. This shaded part I already know. But that's 2, you see. So this part here is 12. So I'm not going to put it down, but we know the area of this shaded part. And this shaded part here, well, when I complete the rectangle, I've got to, that is 2, but do I know this? Well, we got several heights here, or several lengths, if you like. This large one is 6. Now you got another one here, you got another one here, you got another one here, you got another one here. Right? Now watch. This is an important fact here. You see, all these are equal here. You are drawing parallel lines to the base. And you should be able to conclude that these lines are also equal. This and this and this and this and this. All these are equal. All right, so in other words, this diagonal here is divided up into 5 equal parts. Now, if you look at these pieces here, they are growing. This is now growing more, growing more, growing more, and growing more. And they're growing kind of uniformly, right? So it looks as if the smallest one here, right? 1, 2, 3, 4, 5. The smallest one is 1/5 of this, right? We're starting from this one here, and this is slightly more, but they are growing uniformly. So this thing here is 6/5. Divide this entire thing into fifths. This one here will be double that, 12/5. This thing here is 18/5. And this last height will be 24/5. You keep adding 6/5. They're all increasing by the same amount. And now you can see 24/5. When you add 6 to that, you get 30/5, which is 6. So this guess that this is 6/5 is quite correct. So once you got that, then now we can calculate these yellow areas. See? And likewise, you can calculate these other areas. It'll take a bit of time, but you can calculate it. And why? Because each area, like for instance, this yellow area here is half the area of this rectangle. This rectangle, its area is 6 times 2, so this is 12/2, this area. Now here, the area of this rectangle, this yellow part, is half the area of this rectangle. Now we've just worked out the height of this rectangle. It's 18/5, we said. No, 24/5. And the base is 2. So the area of this triangle is half base times height, or half the area of this rectangle, which is, the area of the rectangle is 2 times. So this area will be 24/5. So you can work out each one of these like this. And then, see, the base is 2 in all cases. So so actually, this 24/5, this area here is 18/5, this area is 12/5, and this area is 6/5. Okay? Now, if you look carefully, you'll see that this area is the same as this. So this is 6/5 here. Sorry, the writing has gone too small here. Oh, you can see it. This area here will be 12/5. It will be the same as that. And this area will be the same as that, and so on. So you can work out all the yellow areas here. So the total shaded area you can calculate. You have to add these 10 numbers, right? It'll take a bit of time. Well, it's the last problem. Add these 10 numbers, you get an answer, and that is the area of the shaded area. And if you want to know what the unshaded part is, then you know the area of the whole rectangle. Remember, it's 6 by 10. So what you do, the unshaded part will be 60 minus the shaded part. And that will give you the area that is required. How much larger is the shaded area than the unshaded area? So you take the unshaded, or the shaded, and the unshaded part, and then you find out which is, what are the 2 areas, and then you subtract the smaller one from the larger one to get the answer. All right, now you will admit that this is a very complicated way of doing this, but I'm happy to say that I found a very nice, easy way of solving this problem. And I'm going to show you what I did. Now watch. What's the elegant solution? You see the original diagram. I didn't complete the rectangles. What I did was, I didn't complete it immediately. What I did was I put this, let me just spotlight this thing so that we know what we're talking about. Why is this? All right, okay. Now you see the small area here, I'm calling it 5, I'm calling it area 5. We saw here that that area is the same as this. So I'm putting 5 together here. And then this area here is the same as this. I'm calling those 4. This area is 3, it's the same as this one. 2, 2. And this area here, the first one, is the same as this. Right. So I'm matching these areas, they are equal areas. And then what I do is, now this is the interesting thing, I take the 2 ones and I merge them together because they're the same area. So they are half, this is half a rectangle, there is half a rectangle. And I merge the 2 to get these 2 here. I want to calculate the total shaded area. So I'm going to put entire shaded area, I'm going to reformat them. I take this, I patch it with this, and I get this area here. So the ones are patched. When you patch the 2s, you get this one here. You see this 2 is stopped short here. See? So when you patch the 2s, you get this. When you patch the 3s, you get that. And the 4s, you get that. The 5s you can see clearly. There's 5 here, there's a 5 here. When you put them 2 together, you get this small rectangle. So the area that I'm looking for is that shaded area. That's much easier to calculate than this horrible looking thing here. It's merely by patching equal rectangles, equal right angle triangles to make a larger rectangle. So that's a, even if I were to say so myself, a very clever solution. So now you know in each of these cases, this part here will now you can see clearly, you got all these are equal. You can see this. So this is equal to that, is equal to that, is equal to that, is equal to that. So this 6 here is divided up into 5 equal pieces. And this particular piece is 1.2. See? So we're calling this H. We're calling this height H. I want to avoid the 1.2 for the moment and use a symbol. I do this quite often. When I have the same symbol occurring many times, I use same number occurring many times, I use a symbol for it. And then after that, I will substitute at the end. So I'm calling this H here. Then this will be 2H, 3H, 4H, 5H, as you can see. Oh, wait a minute. Wait a minute. This is H. Oh, the area. The area, this is 2, you see? The length. So the area is 2H. And this area here is 2H times 2H, 2 times 2H, 2 times 3H, 2 times, and that's how you get the shaded area is that. Now each area is equal to 10 because the entire area is 60. Remember, it's 10 by 6. So you got 60 and each area you got, oh, wait a minute. It was 10 by 6, 10 by 6. So the entire area is 60. What am I doing here? So each area should be really 12. So this should be 10. The entire area should be 12. Okay, I'll have to check this thing out. Okay. Um, so 6 times 2. Oh, I see. The H is just one of them. All right, so I just have to be a little bit careful here. And the shaded area minus the unshaded area, and you can see straight away you're taking away this sum here, you're taking away that, and the only thing, all the 2468 at the top, 2468 at the bottom, the only survivor is that one, 10H, and that's the difference between the shaded area and the unshaded area. So the calculation just simply reduces to a very nice number, 10 times 1.2, which is 12, right? So the calculation is extremely easy, unlike the previous case. So this is because I've used a new strategies to solve this problem. Okay, I don't know whether you understood it, but if you didn't, you still got the recording coming up, and I will send you the notes and you can do it. So how many of you actually got the difference is 12? Interested to know. It's the last and the most difficult problem. I'm very happy to see that a number of you actually got the difference to be 12. Okay, so I'm looking forward to seeing many people in this class going to round 3. You're attracting tough problems. Right now we've finished 2018 problems. It is now 16:54, and we can now go on to, we've done 5 problems. Okay. All right, now we go on to the next set of problems. What I've done now, I've finished 3 years of round 2 problems. So I'm not going to do any more round 2 problems. I've chosen problems from my book, and I've selected from problems which I thought were nice, interesting problems, which don't involve too much of mathematics, but just pure common sense and logic. And to see, because ultimately it's all about, mathematics is all about how good are you at thinking, see? How good are you at actually solving problems with very little information at hand and building up strategies? That's what problem solving is all about. So you will see the kind of questions that we got now. I've got no X's and Y's. They're just about thinking. So problem 102, read through that problem. And I'm going to give you a few minutes just to think about the problem, right? While I um, going to go off and grab myself a cup of coffee. For me, it's coffee time. Okay. So you've got this problem, and it's a long problem. Read it and try to understand it. I'll be back. Okay. All right, let's proceed with this problem. You will see I've got P102. So if you want to know the full story about this, you go to my book and type P102 in your search, you will go directly to this problem. And if you type S102, you can go to the solution. So, so you will have the solution in the book. But I'm going to discuss this nonetheless. So let's see what's going on here. You got three people, they are triplets. And you've read the story, so I can just say, yeah, you meet two of them. You don't know who they are. But you know that two of them always speak the truth and one always speaks lies. Right. Okay, now, so one day you meet two of the triplets and you ask them how old they are. A, okay, let's just keep track of A. I'm going to, okay, maybe I'd better put it in here. So what does A say? A says, we are between 20 and 30, 20 and 29 years old. Okay, let me just go to this first. How old are they? Right? We don't know the age, but we'll say, suppose they are X years old. Suppose all the triplets, their ages are X. Right? X is some number. Now what does A say? A says, there it is. We are between 20 and 29 years old, 20 and 29 included. If you put that in mathematical terms, it means your age, your X, is between 20 and 29. Put it 20 and 29. Between. And when you do that, you are actually saying X is like that. X is a number which is smaller than 29, but bigger than 20. This part here says bigger than 20. This part says it's smaller than 29. It's between. But it also says 20 and 30. I'm sorry. 20 and 29 included. Now this is A says this. We don't know whether he's lying or they're speaking the truth, but that's what he says. But we do know that they are between 20 and 30 years old. So this is a fact. Nobody says this. We're told that X is between 20 and 30. I'm going to write it down like this now, explain what this means, because 20 and 30 included. So we know this as a fact. Now this is what A says, but we don't know whether it's true or false. Now B, he makes two statements. He says we are between 21 and 30 years old. So what does B say? What B says? He says we are between 21 and what? 30. And we don't know whether he's speaking the truth here. A liar will always speak lies. The truth fellow will always speak the truth. So he says this, the first statement. And the second statement, he says 21 and 30. And then he says one of us present is lying. He also says one of us present is lying. Right. Now, here at this stage, there's a very crucial question that you ask. Anybody wants to suggest what question must you ask about A and B? We know that we don't know who is lying and who is speaking the truth, but you can ask a question about whether A or B is speaking the truth. So you can ask a question like, is A speaking the truth or is A lying? Or you can ask the question, is B speaking the truth or B is lying? Which question you think is the most pertinent question in this scenario? Okay, there are 4 questions you can ask. But there's one question here which will be very, very informative. I asked the question, is B lying? Is B lying? Now remember, B makes 2 statements. If B is lying, both his statements will be lies. Is B lying?
Sir,
Yes.
are you asking us the question, is B
I'm asking
lying?
you the question, Madhira. Yeah.
I think he is lying.
Yeah, tell me why.
Because in the first part, it says that you know that the triplets are between 20 and 30 years old, 20 and 30 included. But B says that they are between 21 and 30, 21 and 30 included. So it would mean he's lying because
No,
they could also be 20.
no. You see, X could be 25, right? According to B, right? And 25 is a number between 20 and 30.
Sir,
If a number is lying between 21 and 30, it is also lying between 20 and 30. That's an important, right? Come on, somebody else is going to suggest something.
B is telling the truth.
Right, tell me why, Nithya.
I think B is telling the truth. It's because since they both, A and B, have different answers, so one of them has to be lying. And B clearly states
No, you
that
don't
one
know
of
whether
them
one of
is
them is lying.
lying.
You could have, according to the original statement, there are 2 people who speak the truth.
But they
Both of
both
them
have
could be
different
speaking the truth.
answers.
So if they're both.
Okay, answer my question. Okay.
No.
Okay, the next person.
Can I answer?
Yeah, Elizabeth, go ahead.
I feel like B is lying because obviously A went first. So after B had stated
Now,
his answer,
sorry to interrupt. Is it Elizabeth? Yeah. Sorry to
yes,
interrupt. I'm asking the question, is B lying? Okay, now. Okay, so you say he is lying. That's the question. So you say B is lying.
yes,
Tell me why?
because I think he's lying because the reasoning of someone was lying only came up after he stated his reason, after he stated how old they might be.
Prof?
So, can I say something?
Yes, Safi.
So, I wanted to say the reason that one of A or B must be lying is because if person C was lying, that means he would make a paradox. Because if he's telling the truth and he says one of us present is lying, then it cannot be him. I mean, if he's lying, then it means that he's telling the truth, which means he's lying.
Yeah, I think we're getting a little bit closer here now. Right? There's somebody else wanted to say something. Wait, just hold on. Hold on. No hand.
Okay, B is definitely telling the truth, because if he was lying,
that means that his statement, one of us present is lying, would be false. But then it can't be false because he would be
No,
lying.
wait a minute.
So it has to be the truth.
Just say that again.
So B is telling the truth because he says one of us present is lying. So if he was lying, that means that statement would be false because he's lying. That's a lie. So it can't be that he's lying because that statement has to be true.
All right. An important, very important principle. Okay, I'll stop the contributions now. An important principle in mathematics is you make an assumption and use that assumption to come to an impossible situation. And then if you come to an impossible situation, then you will say, my assumption is false. That is why I came to an impossible situation. I'll repeat that. You make an assumption and say, all right, this is what I'm going to say is true. That's my assumption. And then using that assumption, you argue it out and you say, hey, wait a minute. We are contradicting something. There's something that is not wrong, not right. It's going against what we already know, right? And therefore my assumption is false, right? So the starting point, all of you have some idea, but the starting point should be the following. So here it is. Assume B is lying. That's a very, very important starting point. You can say a lot of things and you may be true, but the logic is very clear when you do this. I suppose B is lying. Now, what does it mean? It means that everything he says is a lie. Agreed?
Yes, sir.
Right. Now, in other words, this statement here is a lie. Right? Everything he says is a lie. But we just said that he is lying. If we make this assumption, it is true that one of them is lying. Right? Because I'm assuming this. Under this assumption, one of them is lying. And here, B says one of us is lying. So that means he's speaking the truth. Now he can't be lying and speaking the truth at the same time. I'll repeat this. Suppose you say, assume B is lying. Right. The first conclusion is that, therefore, one of the two is lying, because this is I'm assuming this to be true. One of them is lying. What does B say? B says one of us is lying, which means that he is speaking the truth. But we just said that he is lying. So you can't be lying and speaking the truth at the same time. So that is the thing. I hope you understand that. Think about it. It's tricky. Think about this. So this thing here leads to a contradiction. What do you call a contradiction? And therefore, this assumption is false. This assumption is false. Therefore, B is speaking the truth.
My mic isn't on your phone. I know it's in 15 minutes.
Okay, so B is speaking the truth. And now we come to the second factor now, because we have concluded that B cannot be lying. So B is a truth teller. So there are two statements which are true. This is true, and that is true, because he's speaking the truth now, right? Okay. Now this is true. He's speaking the truth, and he says, one of us is lying. So because this is true, so this is a lie. A is a liar now, because B is now speaking the truth. So A is lying. That's the first conclusion. Let me okay, I've recorded the fact that B is speaking the truth here. Now, what's another truth? Farah, would you please take your mic off, Farah? Okay, so you've got B is speaking the truth. So what's another fact then? Another fact will be X lies between 21 and 30. B is speaking the truth, you see. So this is also a fact. Another fact is one of us is lying. Not him, so A is lying. All these are now facts. So we should be able to put these facts together to find out what X is. All right. So this is a fact. A is lying. So this is a lie. This is a lie. And we know that this is a fact. And this is a lie. So what's the value for X?
30.
30. This is a lie. And this is a fact. So X can't be anything between 20 and 29 because that's a lie. So the value for X is 30.
Busy, go. No.
Okay, Farah, please take your mic off. Okay. All right, so you've got, so I see the 6 people who actually concluded that the area, that the age of the triplets is 30. Right, it's a logical problem. I don't know whether you have used the logic here or you came to the conclusion that B is lying or B is speaking the truth and in some way, and therefore you eventually came to the answer. All right, very good. Let's get on to the next problem. Okay, now we get to this I don't know what number this will be. Right, so we're going to problem number 14, 114. This problem says the square ABCD has length 6 units and M is the midpoint of AB. No diagram is given, so we have to draw it. All right, so you need to draw a square. Okay, and it's called ABCD, so let me just put these symbols, ABCD. Remember, when you're naming a quadrilateral, you name it in sequence. You don't put A, B, C, D. You'll go around like that, or you go in the other direction, it must be again in sequence. M is the midpoint of AB. Okay, I actually want it to be here. So let's just call this, I'm going to rename this thing because I don't have space in my diagram. So if you just, let me just rename this. We'll call this A here. No, BC. No, the A, I'm sorry. A, B, C, D. M is the midpoint of AB, so I got these are equal. This is M. And P is a variable point in BC. need to redraw this thing again. Just one moment, please. Sorry. I wanted P to be on this vertical line. So the original thing was correct. So M is a midpoint here. A P is a variable point in BC. I mean, P could be here or anywhere here. And the question is find the smallest value, and this is M. So let's take a random point, a variable point, like here. Right? And we need to, that's P, and we need to find the smallest value of dP plus PM. So where is dP? dP is here. And PM is that. So you add these two numbers and you want to find the smallest possible value. So how do we go around finding this? There are quite a few P's. You can choose P anywhere here. And each time you choose a P, you got a sum of two numbers. So where must P be so that this plus that is as small as possible? You got lots of possible numbers here. You say dB plus BM is one of them. DC plus CM is one of them, right? Because P can be B or it can be C or the midpoint or anywhere here. But which one gives you the smallest possible sum? So that's the challenge to find this problem, to find this point P. So what I'm going to do is I'm going to just choose P here somewhere. And just P like that. PM, dP plus PM. Now, this is the smallest value of dP plus PM. Look, let me just take a situation like this. Suppose I ask you this question. Suppose I got 2 points. Let's make this thing D and M as before. And I take a point P. dP plus PM. And if P is somewhere here, you'll notice that dP plus PM is always bigger than dm. It's a triangle inequality, what they call the triangle inequality. Two sides of a triangle, dP plus PM is bigger than dm, right? So if I ask, where must P be so that dP plus PM is small as possible, no matter where, if you take it outside this line, you will always get a sum, dP plus PM, to be bigger than dm. So to get the smallest possible value, now this is the crunch of this, the most important point about this. You have to choose P on the line to get dP plus PM to be as small as possible. Then dP plus PM is actually dm. And there can be nothing smaller than dm. dP plus PM is always greater or equal to dm. And when P is on this, then you got the smallest possible sum. Now, in this case here now, I don't have the situation. I don't have this kind of a thing here. So what you do is you actually simulate it. Look, this is not an easy problem, but if you've seen it once, then it becomes easy every time else, whenever you see it again. I'll show you what you do. See, what you do is you take this M, it's a nice trick. You reflect it. You take this M and you reflect it on the other side, across this vertical line. Now, when you do that, it's called this M prime. Then what happens is this length here is the same as this, and this is 90 degrees. And you have an interesting situation that this line here, CB, is a perpendicular bisector of MM prime. Now, I've spoken this about before, and it's a very important fact, and we are seeing it again here. If you take any point on the perpendicular bisector of a line segment, any point, it is equidistant from the endpoints. In other words, these two are actually equal. Right. Now, why did I do all this? Because this dP plus PM in my diagram. Now, notice I said that PM is the same as PM prime. So it's the same as dP plus PM prime. So now you want this dP plus PM prime to be as small as possible, right? And what did I say earlier on? I said that that point must lie, if it lies on this line DM prime, then that makes it as small as possible. Because dP plus PM prime so you will need to have P to lie on this line, on this red line, but it also is constrained to lie on this line. So this is the point that we're looking for. So the point that we are looking for is here. That point gives you the point where dP plus PM prime is smaller than any other point, because this is a straight line, you see. dP plus PM prime is bigger than this. So this is the smallest possible value you can get for dP plus PM prime. So dm prime is the smallest. Is the smallest sum. dm prime is the smallest sum dP plus PM. Right, so now once we got that, then I'm going to delete everything else and ask myself, so what is dm prime? What is that equal to? So if you take everything, whatever I've drawn, if I take it out, and just retain dm prime, right? That will give you the smallest possible distance. So can you calculate dm prime? Well, this is the square of side 6 units. Now we go to what is given. And we were told that the sides of the square are 6. So can we calculate dm prime? Well, you can see it's going to be the hypotenuse of a right angle triangle. We know this side here is 6 because the square has got side 6. And this is 6 here. And this is half of 6 because this is M was a midpoint, you see. So this is 3 here. And that is 3, and that is 3. M is a midpoint. And these two are equal. So you've got that, we've got the other side of the right angle triangle, which is AM prime, which is 9. So dp plus pm prime. So finally, we get to the answer. dm prime is equal to the square root of 6 squared plus 9 squared. That's the other. And that is 36 plus 81, which is 117. So the shortest, smallest possible value of dp plus pm is square root of 117. The answers that you get, I suspect, are all whole numbers. So this is a problem which will not occur. Not these figures might not occur. The same problem may occur, but the figures may not occur because you'll have a nice whole number here. Okay, so that is how you solve this problem. It's quite a challenging problem. And if you haven't seen it before, then it's very unlikely that you'll be able to solve it. But there are other problems like that in the book. You can go and look for them. Just look for smallest value of. Type that in and see whether you can get some other problems which are similar to that, and try to get familiar with those types of problems. Now we go to problem number 115. That's the next problem. Anybody got square root of 117? Oh, quite a number of people. Okay, that's good. It seems that you might have had some experience with this problem before. But if you didn't, then that's excellent. Without any formal knowledge of this, it's a very difficult problem. Well done. Okay, and let's get to the next one. That is the. Okay, we now go to problem 115. Now this time you got a rectangle. ABCD is a rectangle. So let's draw the rectangle as we normally do. Okay. Okay, let's make it a little bit bigger. And P is an arbitrary. Arbitrary means random, any. Arbitrary is an important word in mathematics. It means there's no constraints. You can choose it anyhow you please, right? That's the word arbitrary. So let's just name our rectangle. It's ABCD. P is a random point inside here. Let's just choose it somewhere. Okay, determine PA. So let's write join PA. So we determine this length here, PA, in terms of PB. Okay, so you're joining P, PB, PC, PD. So you got P is all of them. So you're joining P to B. You're joining it to C. You're joining it to D. Right. Now, the question says find this length here. Let's call it X, because we don't know what it is. Let's call this X. In terms of the so let's call this B, C, and D. So we want to get a formula. Determine X in terms of B, C, and D. What does it mean? It means that you want X to be equal to, and you're going to only have B's and C's and D's here on the other side. That means X is in terms of B, C, and D. Now that's very important in mathematics, because then if you know B, C, and D, then you can calculate X. Normally what they will tell you, they'll give you lengths here. This is 7, and this is 6, and this is 8. Find X, right? In a junior paper, you probably will have it something like that. But I made it a little bit more difficult. I didn't give you any numbers here. Instead, I asked you to find X in terms of B, C, and D. Now, how do you go around solving a problem like this? Okay, again, now you have to draw some lines which will make this thing allow us to solve this problem. And you got a rectangle here. So you can solve this problem. It looks as if this B, C, and D are actually, they look like hypotenuses of right angle triangles. So when I say they look like hypotenuses, you can actually make them hypotenuses by drawing a right angle triangle here. See? And here too, you want this to be a hypotenuse. So let's draw a right angle triangle like this. So you have oh, something bad happened here. Why is this? Oh, I know. I chose, instead of choosing red, I chose white. This kind of thing happens to me. Sometimes when you are, red and white are next to each other. Okay, so let's just, I got my red now. So I've got a right angle triangle. I'm going to draw a right angle triangle. And now you can see these are, this becomes an hypotenuse. Oh, it's supposed to be going through this point here. Oh God. Anyway, just imagine this going through this. Sorry about this. Oh, I don't like doing things badly. Let's go back. Rub this out and draw this thing again. Get my line here first, and then draw this thing out like this. Okay, so you got a straight line here, and I'm now going to, while I'm at that, I might as well draw another one on this side here like this. So that I got nice rectangles. I got four smaller rectangles. All these are supposed to be straight lines, by the way. Sorry about this. So these are all 90 degrees. So you draw these. So now these points, your X, B, C, and D all become diagonals of rectangles. But you got lots of other lines here now, lots of other values. Okay, so let's just call these things here. I'll call this P. Let me. So I'm going to bring me even more symbols here. You might say, what's going on here? You're making it very complicated. If you make this P, Q, and R, and S maybe, like that. Then you can see that this is also going to be R here, and this is going to be P here, and this is going to be Q. Okay. In fact, even this is Q here, this red part here, all these are equal. And this is P here. And here, this will be R again, and this will be S. All these will be S. Okay. Now, why have I written all this? Because now I know I can calculate each one of these things. I can calculate the diagonal X squared here, in terms of Q and R, I've got x squared is Q squared plus R squared. But I want to find it in terms of B, C, and D, you see. So at the moment, I've got x squared is equal to Q squared plus R squared, right? And now let's look at B squared. B squared is P squared plus R squared using Pythagoras again. Let's try C squared. C squared is P squared plus S squared. Right? And D squared is Q squared plus S squared. Okay, it looks as if you've got so many unknowns. You've got 8 unknowns. So, oh my God. So this problem is, maybe it's not very fair to ask junior students to tackle this, but we are going to the last session of the last day of our instruction. So I'm going to abuse my position and give you challenging problems like this. And now can I find x in terms of B, C, and D? You'll watch. You got Q squared plus R squared, and you got P squared plus S squared. Now, if you look at these two, you got the whole 4 of them. P squared, Q squared, R squared, S squared. So when I add these two, I got the whole 4. And likewise, if you add these two, again, you got P squared, Q squared, R squared, S squared. So in short, what we are saying is that if I add x squared and c squared, x squared plus c squared is equal to p squared plus q squared plus r squared plus s squared. And that is exactly the same as b squared plus d squared. Because I got p squared plus r squared plus q squared plus s squared. The same thing. And now you want to find x, you can make the subject. X squared is equal to b squared plus d squared minus c squared. Right, so we've got x squared in terms of b, c, and d. And therefore, if you want to find x, you simply say it's equal to the square root of b squared plus d squared minus c squared. So that's x. Okay, so that's, see, all these red lines and all these things all just disappear. You just finally have that this distance here, x squared, is equal to, interesting, it's b squared plus d squared minus this one here. So these two, when you add this squared and this squared, that's what we are saying, x squared plus c squared. This squared plus this squared is the same as that squared plus that squared. A useful thing to know in a rectangle, if you take any point inside a rectangle, and if you look at the 4 distances from the 4 vertices, this squared plus this squared is the same as that squared plus that squared. And that's what we proved here. There it is. And that is how you get x in terms of b, c, and d. All right. So this was a problem. Is there anybody who actually got this one out? Interesting to see as we're getting more and more difficult. Okay, there are still people who are solving these problems. I'm very happy to see that although we are, gone to problem quite far down the line, there are people who are actually calculating these things, which I'm very grateful for, that there are people who are prepared to go on trying the problems that I give you. As long as you try them, then you are learning something. Now, the problem 143 of the book. Again, as I repeat, if you go to the book and click P, I won't do it here because it takes a very long time to search because of all these tablets and everything that I've got here. But when you do it in with your USB, you'll see you'll get very quickly to it. Just type P143 in your search, Control F, and then in that box you put P143. You go straight to problem 143. And this question there will appear, and then if you type S143, or if you click on P143 at that question, if you double click, it'll take you straight to the answer. So you can double click at that question on P143, it'll take you to S143. Or you can put Control F and type S143, you'll still get to the solution. S stands for solution and P for problem. All right, so here you go. There are 100 soldiers in a detachment. Every evening, 3 of them are on duty. So you have a group of 3 people who are on duty at some detachment, whatever that is. Soldiers, okay, so it's an army situation, and you got 3 people who are on duty every evening. So maybe we can just draw a little box there. So there are 3 people on duty every evening. So you got 3 people, you can just call them A and B and C. These 3 people are on duty. Right, now the question is, can it happen that after a certain period of time, some soldier has shared duty with every other soldier exactly once? Okay, so let's just give a name to that. Now, you see, again, you can prove this by contradiction. The question is, can it happen? And then you say, well, suppose it happens. See? And if you come to a contradiction, then you'll say, the assumption is false, therefore it can't happen. I'll repeat that. You say, suppose it can happen. Then you come to something which is impossible, and then you say, therefore my assumption is false. Assumption said it can happen. It's false, therefore it can't happen. See? I like you using that method, the method of contradiction. It happens all the time, and I find it very easy to solve problems like this. So I say, suppose it can happen. So there it is. We'll take, suppose there is a chap here, A. So what about A? This is a soldier. He shares duty with every other soldier exactly once. So A shares, we are assuming that this happens, shares duty with every other soldier exactly once. So what does this mean? It means that on another day, the same A will share duty with 2 others. On another day, he shares duty with 2 others. You got A here, and you got two other guys, B, C, D, E. Like that, it keeps going on like this. Every day, he shares with 2 new people. There are 100 soldiers altogether, right? So what happens now? There are only 99 soldiers left, right? So you can see immediately this, it can't be done, because he is on duty. From 99 people, he selects them 2 at a time, and they all must be new. So that's not possible. 99 is an odd number. You can't break them up into 2s. Right? By breaking them up into 2s like this, then you are saying that the 2 on the first day, plus the 2 on the second day, plus the 2 on the third day, and so on, all of them must be equal to 99. So a number of 2s add up to 99. And that's impossible, because 99 is an odd number. It can't be a sum of 2s, right? So that's the argument. So you can write that in words, and you'll come to some conclusion. I'm not going to ask you, because the argument that you use we have to read it to see exactly what argument you are using before we can say whether you're on the right track or not. But you must listen, read your own thing and ask yourself whether you're explaining it very clearly, that it's not possible to do it. Of course, there are other ways of doing it, and I'm sure some of you figured out some ways of doing that, but I'm not going to ask you how many people have done it. So let's get on to the next problem. Okay, so the next problem is, as I told you now, we have this lovely logical problem. You know, where there's no mathematics. This is the first one of them. Oh, I think it's the first. Where we just argue something out. No X's or Y's or anything. Mathematics is a subject where you're taught how to think. So here's the question. On a chessboard, a knight starts from some square and returns to the same square after making several moves. Show that the knight makes an even number of moves. Very interesting question. So on a chessboard, hopefully everybody knows what a chessboard looks like. It's an 8x8 board. And these squares are all colored black or white. So we're not going to draw this thing in detail, but suppose we take one of these rows. And then you have like that. And then you have that these squares are divided up into 8 parts. Right, now let's see. And of course, these things are colored black or white. So you have the colors are alternate, black, white, black, white, black, white. A chessboard is always covered like that. Sometimes I've seen chessboard with brown, white, or brown, some other color, but the standard chessboard is black and white. Now, a knight. And the knight in the chessboard is the horse. And all of you have gotten the second round, so there's a good chance that you already know what the knights are. But just in case, let me tell you how a knight moves. A knight moves like this. It starts from some point. It moves 2 units along one direction and 1 unit in another. And so you can move from here to here. Or you can start here and you can go up like that, there. Or you can do this. Or you can do that. So it's L-shaped. Right? Starting from somewhere, you can have a long L first or a short L first. You can have a short L like this and going. So you're starting. It's called a start. And this is end. So that's how a knight moves. So it starts from some square. So, okay, suppose he starts from the square here. Right. Now, he goes all over and he returns to the same square. He goes on a nice travel. From here now, he goes to this maybe. And then he goes to that. And then he goes to that. And maybe it goes 2 units down. 2 units. Comes down, he finishes here. And he does all these things. And in the end, he lands back at the square here. So he makes a number of moves. Right? We don't know how many. But he comes back to the original square. Now the question is, show that he makes an even number. Okay, I'll leave the floor open. Guys, you can put your mics on and let's see if anybody can argue this out?
So,
Right, nakshatra.
can you not just move it to another square and then back? Because that's still 2 moves.
That's right. But the question is now that you're making a very specific move, right? But that thing doesn't tell you that you're going to a square and coming back. It says you travel around. You can. Okay, for that particular move, you got an even number of moves. But how do you know that if you take some other route and you go all over the place, you travel all over the chessboard and you come back, that the number of moves you make is even? That is the question. You understand, Nakshatra?
Yes, sir.
Right? Anybody else wants to? But thanks for that, Nakshatra. Nakshatra says that you can take one particular example and you'll see it's even, right? Okay, I don't know what the names of the people are. If you can talk, then I will. Right, okay. Talk, please.
Okay.
Andre.
So when the knight moves, when it moves a certain number of moves away from where it started, it has to move the same amount of moves to end up back where it started. So if it makes 2 moves, it has to make 2 more moves to get back to where it was. And that's
you're kind of. How do you know? It's not just 2 more moves. You can then from the, you see like what I've got here now. You can have several 2 more moves, you know. See, you can move here, right? Then you can move here. Then you can move here. Then you can move here. You can move many moves. You don't know how many moves. You may take 100 moves. You can go all around and refuse to come back. But eventually it can come back. The total number of moves that it makes, you want to prove that it's an even number of moves. Okay, anybody else now wants to try?
Sir,
Yes, Georgia?
is it even because he moves from a white square to a black square and then from white to black and then white, black, so it's even?
Now we're getting somewhere.
Prof, is it not because he moved from a white square to a white square and a black square to a black square?
No, he moves from a white. You see, if this is white, this will be black. This is white and this is black. You see, these 2 are the same colors, but these 2 are opposing colors. So he moves from one color to its opposite color. You could start from a white to a black or a black to a white, because the knight always moves from one color to another color. The same color will be here, but this will be opposite. Okay? All right, so Georgia got a very interesting point. She says that each time the knight moves, it changes color. Right? Each time it moves, it changes color. If it's coming back to its original position, it comes back to its own color. So when it changes color, to get back, if it was white here, to get to a white, it has to make 2 moves. The first move will be to a black. So somebody start with white here. White. Let me just put the colors instead. Just one moment. Okay, now suppose okay, starting here now, right? This is, suppose he starts white. Then he goes to this, which is black. So when he makes 1 move, he moves into a black square. But to come back to white, he has to make 2 moves. Every 2 moves, he comes back to the same color. If he makes an odd number of moves, he moves into an opposite color. But when he moves 2 moves, it comes back to the same color. This white, he has to make 2 moves to come back to white. And he has to make another 2 moves to come back to white. He eventually lands up with white, on white. So he must have made a several number of pairs of moves to come back to its own color. So therefore, the number of moves will have to be even. So you have to argue that out that each time he moves, he changes color, but that's not enough. You must say each time he moves, he changes color, but he has to move 2 moves to come to the same color. Every 2 moves, he comes back to the same color. Since he eventually comes back to his starting point, right, he must have made several number of pairs of moves to come back to that. And a number of pairs of moves will be an even number. All right. Now, those who understood that argument, please raise your hands. More people should be raising their hands if you didn't understand that. Okay, so a number of people understood that argument. Okay, that's great. Okay, but if you had 69 people, or the rest of you are, or you don't understand it? Come on, or you're just sleeping, you refuse to raise your hands. Okay. Don't be lazy. I ask you to raise your hands if you understood. You put your hands up. Don't just look there and yawn. The next problem we are going to do is problem number 145. A certain country has coins having values 1, 3, and 5. You see, when you argue this out, I want your language is quite important also. You need to have some kind of language proficiency to argue this thing out logically so that the person who's reading it follows the argument that you're using and says, yes, he knows what he's talking about. Right? And you have to explain it in a proper way. So this is a language kind of a problem. So let's go back to this. You got a coin having values 1, 3, and 5. Can one make change of a 25-cent coin using in all 10 coins, each having the value 1, 3, or 5? So you want to use 10 coins, and the values of the coins are 1, 3, or 5. And can you get some combination of 10 coins with these numbers to get 25 altogether? Okay, anybody who wants to try?
Sir?
Duncan?
It's not possible because if you added 10 odd numbers, you would get an even number, and 25 is an odd number.
Right, excellent, Duncan. So he says, if you're adding 10 numbers, all of them are odd here, 1, 3, 5. So you're adding 10 odd numbers. We don't know what the numbers are. So again, it's proved by contradiction. You say, suppose it can be done. Suppose it can be done. Can one change? You see, this is a question. So you say, all right, suppose you can. Right. Then you're adding 10 odd numbers and you're getting 25. And Duncan says, when you're adding 10 odd numbers, you're going to get an even number. What's the reason for that? Because 2 odd numbers will give an even number. Agreed? Agreed. If you're adding 2 odd numbers.
Yes, sir.
Right. And then now you got 10 odd numbers, so you got 5 pairs of odd numbers.
Yes, sir. Oh.
Which means you're adding 5 even numbers. Right? And when you add 5 even numbers, you can never get 25. The sum of even numbers is always even. So if you assume that it can be done, you'll prove that 25 is an even number, right? Which is impossible. You see? Hey, this is impossible. It's a contradiction. So therefore, our assumption that you can get 10 odd numbers adding to 25 is false. Therefore, you cannot make such a change. You see, that's the argument. Just understand the logical argument in this. Assume the opposite and come to something which is impossible. And then you say, the assumption that I made is false. All right. Okay, so let's get on to the next one. The next problem is, oh, my goodness, we've actually exceeded our time. I thought I had all the time. It's not very nice. Okay, sorry, I've exceeded my time. I took too long over this. There's 152. It's an interesting problem. I'm going to explain this thing here because we haven't done any problems like this. So I'm going to take maybe 5 minutes to just give you the background to this. What you can do is look at study the book. This is, I want you to go to the book and get this thing, a number of factors. I have a small section which is entitled something like this, the number of factors. So you type number of factors, or you go and look at the index right in the front, look for anything which says number of factors, right? Now there is a formula for the number of factors for a given number. Now, look, I'll give you an example. You can read through this thing here and you will see where it's coming from. Suppose you want to work out how many factors does let's take a number like 18 have. How many factors? Well, if you take the factors of 18, one is certainly a factor, and write the other factor down, 18. Right? 2, the other is 9. 3, yes, 3 times 6. 4 is not a factor. 5 is not a factor. You can go to 6, but then you get 6 and 3, so you'll come back to the same ones which you've already got. So there are 6 factors. Right? 6. The answer is 6. Now there is another way of doing this. Now this is what we are going to use now. You factorize 18. 2 times 9. That's 2 times 3 times 3. That's 2 times 3 squared. You write it as a product of powers of prime numbers. You must write it like this. Right? So now you got the product of powers of prime numbers. When you write it like this, then the number of factors, there's a very nice formula, equals. Now you take the index, you see it's 1 here, index. In the factorization, take the indices only, and you increase each index by 1. 1 plus 1. Put a bracket around that. Multiply it by, now do the same thing to that index. And add 1 to it. We stop right here because you only have got 2 indices. What is this? This is 2 times 3, and there it is, 6. You can get to this answer by the simple formula. See? Like now, if I take, for instance, take a number like 72. I say, how many factors does 72 have? 72 is 8 times 9. 8 is 2 cubed. 9 is 3 squared. So this is the way you write 72 as a product of powers of prime numbers. Factorizing, this is the best way to factorize it. Product of powers of prime numbers. How many factors? Number of factors that 72 has. You can list them down, but there's a very easy way of doing it. 3 plus 1. Increase that by 1 and multiply it. 3 plus 1 is 4. 4 times 3 is 12. So 72 has got 12 factors. See? So that is how you work out the number of factors of a number. There's a simple formula to do it. And that is what you use to solve this problem. Okay. So now, the question here is a little bit more complicated. It's to find all numbers less than 50 that have exactly 4 factors. So what have we got? So we'll say, let the exponents Okay, let's put it this way. Let's put it this way. Suppose n is such a number. Sorry, my writing is atrocious. Suppose n is such a number. Now what do? We write n as a product of prime powers. Let's call it p. And you have an index. And you put another prime number here, q. You have index. And you go on, you write all the possible prime powers. And then to find the number of factors of n, now we know that n has got exactly 4 factors. So the number of factors of n, you can put on 4 straight away, is equal to a plus 1 multiplied by b plus 1 multiplied by maybe c plus 1 and so on. Now, in other words, 4 is factorized into several numbers, right? Now, what are the factorizations for 4? The factorization for 4 are 1 times 4 and 2 times 2. Those are the only 2 factors for 4, right? Those are the only 2 factors. So it means now that you could have so it means now that a plus 1 is equal to 1 and b plus 1 is equal to 4. You could have that situation. Or you could have a plus 1 equals 2 and b plus 1 equals 2. Because you're multiplying these to get 4. This first thing here gives you that a equals 0. This one here. And b equals 3. And this thing here gives you a equals 1 and b equals 1. See? Now how do you translate this into our problem? Our problem is you needed to find these factorizations. So you got n is equal to, now here, a is 0, p to the power of 0, and you only have one more, q to the power of 3. So n is q cubed. So n is going to be equal to q cubed, where q is a prime number. And in the second case, you got n is equal to, a is 1 now, and b is 1. So I'm not going to put p to the 1, I'm just going to put pq. A is 1 and b is 1, it stops there. So, where p and q are primes. Right, now, I'm sure many of you are already lost, but please go and go back to this problem and try to follow the logic of this. Now, this thing here, you now say, what do we mean by this? We are saying that either n is a power of a prime number. So now what are the powers of prime numbers? You got 2 cubed, which is 8, 3 cubed, which is 27, 5 cubed, but it must be less than 50. This is too much. So the only prime powers which will fit this bill are 8 and 27. So n could be 8, could be 27. And if you try these, you will see they've got exactly 4 factors. You can check it out. This has got 4 factors. This has got 4 factors. That takes care of the first one. The second one, you got n is a product of 2 prime numbers. And in this case, you have many, many numbers. Because your first prime number could be 2, and the second prime number could be 3. That gives you 6, 2, Second prime number could be 5. 2 times 7. So if your first prime number is 2, you go all the way up to 2 times, you want it to be less than 50, and 2 times 23 is 46. And you go to past that, you go to 2 times 24. Well, your prime number, the next prime number is 2 times 29, which is too much. So you got all these, and then you can try 3 times something. Now don't include 2 now. So you have 3 times 5, 3 times 7, right? And you'll have to go up to, you can't go beyond 50. So you probably have to go up to 3 times 13 is 39. And after that, 3 times 17 is too much. So, okay, you need to, the question is find all numbers less than 50 that have got exactly 4 factors. So you list all these numbers. There are quite a lot of them, and there will be 15 answers. There are exactly 15 numbers less than 50 which have got exactly 4 factors. You could do it in the long way. Take all the numbers and find out how many factors it's got. It'll take you a long time because there are 50 numbers to go through. But if you use this logic, you can reduce your search considerably. See, because you can identify precisely those numbers which have got less than, which have got exactly 4 factors. Okay. Oh, you see, I took a tea break and all that. So that is so bad. I thought I had a lot of time. Okay, this one here is quite easy. I'll just give you the hints here. You see, when you got 10 factorial over 9 factorial, you got one more here, and you're dividing by this, right? Now, when you got 10 factorial, for instance, you got 1 times 2 times 3 times 4, all the way up to times 10, right? We've done this before. Remember, we said factorial. You read this as factorial, 10 factorial. 9 factorial, we've done this before, 1 times 2 times 3, all the way up to 9. And then you can see that all these will cancel. The only survivor is 10. So when you go 10 factorial, everything before that will cancel. Here, 8 factorial, everything will cancel. The only survivor will be 9. So you're adding 8, 9, and so on, all the way up to 2. And you just add up these numbers, and that will give you the answer to this problem. The crucial thing is, all these things are just equal to, you can see 9 times, all the numbers below 8 is 9 times 8 factorial, and the 8 factorial cancels. This is 8 times 7 factorial. So the 7 factorial will cancel. So that's how you do that one. That's not difficult. And then the next one, oh, I think this is the last one, or maybe not. This one here was quite a challenge. I don't know how many of you actually tried this problem. And I must confess that I tried it many times, and I only got the best solution after a lot of tries. What this problem is saying is that you got a square of side 17 centimeters, and you divide each side into 4 equal parts, as you can see. So all these are equal. So you got 17 here. So each one is a quarter of 17. And you do this right round, and then you join all these things like this, and you get a new setup like this. And you got a tilted figure, which is a lot of small squares. And they tell you, they ask you, what is the area of this part here? And the solution that I got, right, I'm going to tell you how to do it, and then you can check out how to eventually get to the answer to that, right? Because we don't have enough time, unfortunately. The solution is, you see this part here, in fact, these squares here are part of a larger square. And I draw the larger square. I make this a side of a larger square. How do I do that? I go down, I go down here like this. I have to extend this line a little bit here. And then complete this thing. All right, so now you got this, you see you got the square here. And the question is now, if I can find the area of this square, then this part here, this square here has got 16 squares in it. So the area that we're looking for, the area of this yellow part, is a quarter the area of this new square. So the problem is to find the area of the new square and find quarter of that, right? And to do that, you say, okay, let this little part here be x. See? Then you will have that this is x. All these parts are equal. So this side here, the side of the new square, is 4x. See? So you need to calculate, the side of the new square is 4x, and the problem is, what is 4x squared? That will be the area of this new square, and we're looking, the yellow part will be a quarter of that. So all I need to do is to calculate x squared, or x, because this one here is 16x squared, and a quarter of that is 4x squared. So I need to calculate x. How do I calculate x? To calculate x, notice that, you see, this is x here. So this part here is also x. The rectangle here. See? Now remember, we said that this was 17. The original square got 17. So if you look at this right angle triangle here, you got that this part here is 17, this line here. And this part is 4x, because this is the side of this new square. So you got a equation here. You got this side of the square is 4x, this is x, and you got a right angle triangle. The hypotenuse is 17. So when you use Pythagoras, you got 16x squared plus x squared is 17x squared. See, and the 17 fits in nicely here, because this is 17 squared. That's the square of the hypotenuse. 17 cancels beautifully, and so x squared is 17, and 4 times 17 is 68, and that is the area that we're looking for. This by far is the simplest solution. Even the people who have put the solution on the website, they didn't come to this conclusion. So I'm quite happy with this. It took me a long time to get to this beautiful solution. Okay, so the answer is 68. I don't know how many of you actually got 68 in this, if you went this far. Sorry, a number of people are leaving, but there are still people who are remaining behind, which I'm grateful for. Today is the last day, so we want to finish off these problems. And let me see if there are any others. Okay, and the next one. Okay, just ignore that telephone, I didn't switch it off. Now here you've got a diagram, and they show you, they say the area of the largest square is 64. So the area of the largest square is 64. And then we construct another square inside it. And the way to construct the square is you take a quarter length here, you take another quarter here, and take another quarter here, take another quarter, and you join these 4 points, and you get a new square, right? And then you do exactly the same thing to this square to get You take a quarter here, a quarter, a quarter, and a quarter to get this inside square. They tell you the outside square has got area 64 and find the area of this inside square. So that is the problem. It's an area problem. Okay. So we can do the following. Now watch. I want to find out what is the area of the first square. The first square is 64. What is the ratio of the area of this first, the middle square, to the area of the original? See? Then whatever that ratio is, this ratio will still be the same because you're doing exactly the same thing to this inside square. So the ratio of this square to the original, to the second smallest to the middle, will be the same as the middle to the largest because the construction is exactly the same. See, and that is really the key point. So to find that ratio, if you call this x here, this will have to be 3x because it's quarter, and this x here, and this will be 3x, right? So what is BE squared? That is the area of the square. Square, we'll call it square 2. You got square 1, the largest one. Square 2 is the second one. And this is square 3. Square 2, area of that is BE squared. See? BE squared. But now if you use Pythagoras, you got 3x here, you got x here. 9x squared plus x squared is 10x squared. So the original square the area was AC squared. This is 10x squared. AC squared is 16x squared. So the original square, because you got 4x here. So the ratio, the second square is 10/16 of the original, which is 5/8 of the original, right? And the original is 64, and then you get 40. So this thing here is 40, and this also will be 5/8 of 40 because the construction is exactly the same, you see. You're still taking quarter, quarter, quarter. So you're not doing anything different. So this area will be also 5/8 of 40, and 5/8 of 40 is 25. That's the answer to that problem. Okay, so I'm going through this thing rather briskly, and I'm sure you'll be able to understand it. Oh, I had quite a few problems. I didn't realize I had so many. Oh, so this is the last one. Fortunately, this is the last one. And I'm about to finish. And I think we've done this kind of thing before, right? You've got a regular polygon. Actually, it's a pentagon, 5 sides. So I really should have had a regular pentagon here. Now we've spoken about regular figures. This should have been pentagon. It's got 5 sides. It's a very easy problem. I'm giving you the solution rather than the question. Sorry. Okay, let's just. I did have pentagon. Okay, what is the size of the angle marked X? Okay, look, this is, we've done this thing before, and a regular picture. I've told you how to find all the angles of a regular polygon, right? And if you went over that, you will see that the way to do that was the exterior angles, they're all equal, and they all add up to 360 degrees. So you've got 5 exterior angles, which add up to 360 degrees. They're all equal, right? So each exterior angle, 5 of each exterior angle is 360. So each exterior angle would have been 360 divided by 5. And when you work that out, you get 72. So the exterior angles are 72. So therefore, these two things add up to 180. So the interior angle is 108. All the interior angles are 108. In particular, angle A is 180, but a regular figure all the sides are equal. So if this is 108, then these angles will be equal. They add up to 72, right? Because this is 108. So x must be 36. So this is a standard problem on regular figures. Just remember that the sum of the exterior angles equals 360 always for any polygon. In a regular one, all of them are equal, so you can calculate each of the exterior ones, and therefore you can calculate each of the interior ones. And once you do that, this problem now becomes quite easy. Okay, guys, I see from our original class of 60 something, it's reduced to 37. I don't know how many of you went all the way up to problem 551. If you did, how many of you got this problem out? Okay, so there are many people who actually went up to this and you tried it. And for any regular pentagon, any regular figure, you should be able to do it. Now you see, now you're writing on Tuesday and you've got today is Thursday, and just find some time to go over all the problems that I have done, right? We'll try to, today is Thursday. I'm going to ask the people to put down the solutions tomorrow morning for session 4. So you'll have all the solutions, and please go over all the problems that I have done so that you familiarize yourself with every problem. By the time Tuesday comes, you must tell yourself, I know how to solve all these problems. Do it yourself, try it, check the solution. Do it yourself, try it again, check the solution. If you don't get the solution, again, look at the solution. My technique is, once I've got the solution, I rewrite it. That's how I learned mathematics. I rewrite the solution all by myself without looking at it, right? Having seen the solution, don't say, oh, no, I can't understand it, and get on to the next one. I close the book and say, I'm going to write the solution all over again, right? I'm giving you a very, very important clue on how people become professors of mathematics. Because you do it yourself. Even after you get the answer, do it yourself. And then you know that you have done it and you know how to do it. Right? So do that. That's an important clue. And you will be, if you can do the whole lot, then I can assure you that without a doubt, you'll be able to get into round 3. So you have everything in front of you. All you have to do is to work hard at it now. Because as you do each problem, you get new strategies. You get a new idea of how to solve a problem. You won't have the same problems coming up in the paper, but you'll have familiar situations. And you'll say, wait a minute, I remember one of the problems the prof did looked like this, and this is what he did. You see, so you have a strategy, and then that will help you to solve those problems. Okay. Remember, the most important thing in problem solving, I always say, is there is an X somewhere. Create an equation, somehow create an equation, solve for X. Right? That's the whole idea in most problems. See, like in this problem here, the equation is 2x plus 108 is equal to 360 degrees. You see, x plus 108. That's your equation. And if you solve for it, you'll get x equals 36. So there's always an unknown, and give names to the unknowns. Okay, so I'm getting out of stop share and I'm going to talk to you guys. All right, I just want to tell all of you guys, you are the last survivors. We had almost 200 people in the beginning, and there are only 37 people who lasted the distance. And I suspect that many of the 37 people here are really interested. So you think you can make it. And there will be other people who are saying, well, we have the recording, so you can go and check the recording. We don't have to attend the class. That's fine also. But I wish you all the best. Sura says, thank you for this training, Paz. Highly appreciate it. Okay. Okay, a lot of people, some people are saying thank you, appreciate it. Okay, no problem. I enjoy doing this. You can see I'm very passionate about problem solving. So the joy is mine as much as it is yours. So thank you for thanking me. Okay. All right, I'm going to stop there and ask if there's anybody who's got any questions. You can feel free to ask it now.
Sir?
Yes, Duncan.
I'm still in grade 7 and doing the junior Olympiad.
Oh, you're grade 7?
Yes.
Oh, that's... now tell me, Duncan, you as in grade 7, you still stuck around till the last bit here. Were you able to follow some of the things? Because...
A few of them, sir.
Okay, that's fine.
Algebra.
That's fine. If you can solve, if in grade 7, if you can still understand grade 9, with people sitting grade 8 and grade 9, then you're okay. That's good. What do you want to ask, Duncan? You just want to tell me that in grade 7?
I'm asking your ebook.
Yes.
Like, what level questions must I practice for the Olympiad?
Oh, I see. Yeah. Now, it's hard to say. You see, as the problems go further down the line, by 20, 21, 22, up to 25, the levels become higher. The levels go up to, maybe it'll go up to level 5 in junior, maybe occasionally level 6, but I think most of the time it'll go up to level 5. Those are harder problems. But I think if you stick around at level 4, maybe level 4, level 5, try those problems, occasionally a level 3, then, okay, it's good you're asking me that. So, you will know which ones to look at. But I would suggest that you do level 3, level 4, level 5. And if you can tackle a couple of level 6, which are familiar, you see, wait a minute, Prof did this kind of a thing, I can try that, right? Those problems might occur in the upper levels at 21 to 25. Okay, Duncan?
Yes, sir.
Right. Any other questions?
Sir?
Yes, Pooja.
I just wanted to confirm that we wouldn't be getting questions like P143, P144, and P145, where it says, can this happen or prove that this happens?
Yeah. You're quite right. Right.
Okay, thank you.
Yeah, there wouldn't be any such question. They're fine. Everything is a single answer. Okay, those were meant for your edification, to give you logical problems on how to argue, right? So they might not occur in this paper, but I thought I'll use this opportunity to give you some logic, because mathematics is all about thinking and logic and using evidence in front of you to solve problems. Elise Chen?
Sir, I
Yes.
have 2 questions.
Yes.
Where can you find the recordings?
It will be on the Google Classroom. The recordings of all the other 3 are already on it, right? And today's one. Hopefully it will go tomorrow.
Okay. Second question, where can I find your book? I can't seem to find it.
Oh, is that Luke?
Yeah, Luke.
If you registered, write to Ramaboka. He's one of the persons who communicates with us. Just write to him and tell him you don't have the book. Please give me the book. He'll give you a link, and that will give you the book. Okay.
Okay.
All right.
Thank you, sir.
Okay, look. Are there any other questions? Okay, Norhan says, okay, he thanks me very much. No problem, Norhan. Okay, bye, Alice. Any other questions? Okay, it seems that there are no other questions. So we will close the session here, and bye. Bye, everyone.
Thank you, sir. Bye, sir.
Okay, bye,
sir.
Akil.
Thank you.
Bye, Akil. Bye, Duncan.
Thank you, sir.
Bye, Nakshatra.
Bye, sir.
Bye, Gabriela.
Bye, sir.
Bye, Haley.
Bye. Good night, sir.
Good night. Good night, Haley. Yes, Dylan, who are the people who raise their hands? Oh, sorry, Renono, you raised your hand. You want to tell me, you can talk to me if you want, Renono? Or you lowered your hand now? Renono? And Nokan Koba, you also raised your hand?
Sir, I'm failing to log into the SAMF website.
You're failing to log in to the
I'm
website?
failing to log into the
SAMF
website. Yes. It says my email is wrong.
It's www.samf.ac.za.
I did try, sir, but it still refuses.
Oh, that's strange. There's something, I don't know. I cannot answer that question. You should be able to do that. Maybe you don't have internet access or something like that. But if you got internet access, that will take you to that. Just check it out. Okay. Matata, you got a question?
Yes, sir.
All right. I think there are no other questions. We will close the session. Thank you very much.